Okay, so let's start. What we'll do today is first we'll look at some of the questions from week four's assignment. Then we'll look at some related questions from week four's content. And in the last 45 minutes or so, we would look at the uh, problems from week five's content. Okay. Someone who's in the chat. Okay. So let's start. Okay, so the first problem is so the first five or so problems are from week four's assignment. You might have already solved these. So if you know the answers, you can write the answers in the chat. Okay. So the first question is, which of the following is or are true about the modes of operation of block ciphers? The options are a sequence of n messages requires at least n calls to a PRF for encryption. Option B is ciphertext computation is parallelizable in the CTR. Okay. Let me try to rejoin. Hello. Is my voice better now? Oh, great. Yeah. Okay. Okay, I'll repeat the first question. So, which of the following is or are true about the modes of operation? The first option is a sequence of n messages requires at least n calls to a PRF or a pseudo-random function for encryption. Option B is ciphertext computation is parallelizable in the CTR mode. Plain text of any length can not be encrypted using the OFB or output feedback mode. And stateful variant of the counter mode is secure, but the stateful variant of the OFB mode is not secure. So you might have already solved these in the assignment. So would you like to tell me what the answers are? You can write the answers in the chat if you do. Yeah. Okay. So A is correct. A is one of the correct options. Are there other options which are correct as well? Okay. So yeah, the answers are so that there are three options which are correct. Uh, A is correct, B is correct, as well as as well as yeah, A and B are both correct. Wait, did someone write something in the chat? Okay, yeah. Okay, so like in any mode of operation, to encrypt n messages, we at least require n calls to the PRF. That is true. And inside, so in the counter mode, what we do is the following. So we have C0 is equal to let's say some initial value of the counter. Then to obtain CI, the ith like ciphertext, what we do is mi XOR fk of CTR plus I. So let me just call this CTR. So this is what we do in the CTR mode. Now, since we can compute all these in parallel, we can actually parallelize the computation of ciphertext in the CTR mode as well. So options A and B are correct. What about option C? Plain text of any length cannot be encrypted using OFP mode. That is incorrect because OFP mode and CTR modes can give you string ciphers. So you can encrypt messages of any length using OFB and CTR mode. And option D is the stateful variant of CTR mode is secure, but the stateful variant of OFB mode is not. That is also false because the stateful variants of both the CTR as well as the OFB mode are secure. However, the stateful mode of CBC mode is not secure. Yeah. So the correct answer over here is A and B. So if that's fine with everyone, we can move on to the next problem. So the next problem is select the incorrect options from the following. The options are A, assuming all block cipher constructions are secure PRFs, they are CPA secure as well. Option B is assuming a secure PRP, that is pseudo-random permutation, is used in the construction of the stateless mode of CBC is CPA secure, but the stateful version is not. The option C is assuming a secure PRF or pseudo-random function is used in the construction. The stateless mode of OFP mode is CPA secure, but the stateful version is not, and none of the above. So which of these options are incorrect? Okay, yeah, so options A and C are incorrect. So just because we are using secure PRFs does not mean that we can get CPA secure encryption schemes using all modes of operation. In particular, if we were to use, say, the electronic codebook mode or ECB mode of encryption, then no matter whether we are using a secure PRF or not, we are not going to get CPA secure scheme. And similarly, if we are using the CBC mode, the stateful version of CBC mode, then also secure PRS are not going to give us secure block ciphers, CPA secure block ciphers. Option B is assuming a secure PRP is used in the construction. The stateless mode of CBC is a CPA secure, but the stateful version is not. This is true. And this we saw in the class. Option C is assuming a secure PRF is used in the construction. The stateless mode of OFB mode of operation is CPA secure, but the stateful version is not. This is also false because for OFP and CTR modes, as long as we are using secure PRFs, both the stateless and the stateful modes are CPA secure. So both A and C are incorrect options. Is this fine? Okay, so then we can move to the next problem. So the next problem is which of the following is or are correct? An R round substitution permutation network has R rounds of key mixing, substitution, and permutation. Option B is SBox is used in an SPN, that is a substitution permutation network, are always invertible. Option C is a three-round fiscal cipher network is secure, whereas a two-round network is not secure. And option D is since the components of the fiscal network are not necessarily invertible, the fiscal network itself is also not invertible. So which of these are correct? Okay, so the only correct option over here is C. Okay, no wait, B is not correct. So B is not correct because if you recall the S boxes that we used in while constructing DES, those S boxes were mapping 6-bit inputs to 4-bit in outputs. So they cannot be invertible because yeah, the The number of strings of length 6 is like 2 to the 6. The number of strings of length 4 is 2 to the 4. So since the size of the codomain is less than the size of the domain, you cannot have an invertible function. So S boxes need not always be invertible, but if you want to create a practical pseudo-random function using SPA, sorry, if you want to create a practical pseudo-random permutation using SPN, then yes, your S boxes in that case need to be invertible. Okay, so option B is incorrect. What about option A? An R round substitution permutation network has R rounds of key mixing, substitution, and permutation. Well, this is almost correct. It's just that an R round substitution permutation network has R rounds of key mixing, substitution, and permutation along with a last mixing step, last key mixing step. So yeah, just one step is missing over here. Otherwise, this would have been correct. So A is not correct, B is not correct. C, we saw in class that Fistel cipher is with just 2 rounds is not secure, but with three rounds is secure. So C is correct. And option D is since the components of the Fistel network are not necessarily invertible, the Fistel cipher itself is not invertible. Okay, this is false because we saw in class that to invert a Fistel network, all you have to do is like apply it in reverse, right? So Fistel network is invertible regardless of whether its components are invertible or not. So option D is also not correct. Is this fine? Yeah, so if this is fine, let's move on to the next problem. So given Fk is a secure PRF, define a new function, new keyed function, f prime k of x as Fk of x is x if x is even and Fk of x plus 1 if x is odd. So which of the following options are correct? Option A is the new PRF, that the new function, that is f prime k is not a secure PRF. Option B is f prime k is a secure PRP. Option C is f prime k cannot be used to instantiate the OFP mode of operation. And option D is f prime k can be used to instantiate the CTR mode of operation. So which of these options these are correct? So you are saying that B and D are correct. Okay. So yeah, actually B and D are incorrect. The correct options are A and C. Here we are supposed to select correct options, right? Okay, so let's see why. So let's see why this is not a secure PRF. So for a function to be a secure PRF, no PPT adversary should be able to win the indistinguishability game for PRFs, right? So what we'll do is we'll just construct an efficient adversary that wins that game, and that would prove that this function is not a PRF. So we have the verifier, we have the distinguisher, and here's what a distinguisher does. It just sends x 1 is equal to 0 to the n minus 1 1 and x2 is equal to 0 to the n minus 2 1 and 0. So x1 is just 1 in binary and x2 is just 2 in binary, right? And over here addition is like let's assume that fk is from 0 comma 1 to the n to 0 comma 1 to the n without a generality. So uh, our inputs would be n-bit strings, our outputs would also be n-bit strings, and this addition is going to be modulo wait, this addition is going to be modulo to the n. Okay, so x and so x is going to be a string of n bits, but that you can also interpret as a number in binary, right? So if that number is even or that number is odd, depending on that we define f prime k. Is this fine?
So number of ones And we are
No, not the number of ones. So X is a binary is a bit string, and let's say X looks something like this, right? 0, 1, 1, 0. Then X is a binary string, but you can also interpret X as as a binary number, right? For example, 0, 1, 1, 0 is both a string and a number. As a number, it's what? 6, right? So if that number is even, so over here by X is even, we mean that that number is even. Is this fine?
okay. Okay.
Yeah. Okay. Yeah. So the distinguisher group is going to send x1 is equal to 0 to the n minus 1, 1, and x2 equals to 0 to the n minus 1, 1, and 0. So as numbers, these are just 1 and 2. Now what will the verifier do as usual? Toss a coin. If uh, p is 0, then yi is going to be, so it's going to play with a totally random function. And if b is 1, it's going to pick a key uniformly at random from 0, comma 1 to the n and set yi to be, oh wait, I was using capital, yeah, capital, 5k of xi uh, for all I, for I equals to 1, comma. Then it's going to send y1 and y2 to the distinguisher. And here's what the distinguisher will do. It will check if y1 the same as y2. If yes, it's going to set p prime to 1, and no, it's going to set p prime to 0 and send b prime to the verifier. Okay, so now let's analyze the probabilities. So probability that p prime is equal to 1 given b equals to 1. So when b prime is 1, sorry, when b is 1, uh, f prime k of x1. So x1 is a binary number is 1, right? And since it is odd, f prime k of x1 is just going to be fk of 2, right? And f prime k of x2. X2 is an even number too, so this is also going to be fk of 2. So when b equals to 1, y1 and y2 would be the same. So this probability is 1. And what about this? The other probability? Okay, so when b is equal to 0, y1 and y2 will be independent random strings. So this probability y2 equals y1 when both are random. And this would just be 1 over 2 to Tn because fix any value of y1. The probability that y2 would be that value is 1 over 2 to Tn. So this difference, and this is non-negligible. So we have constructed an efficient, okay, so it's clear that D is efficient. So we have constructed an efficient adversary or an efficient distinguisher that can distinguish between f prime k and a truly random function. So f prime k cannot be a PRF. So option A is correct. It's not a secure PRF. Now, why do you think it's a secure
You are not.
PRP? Because someone said that B and D are both correct. So why do you
You are
think it's
not audible.
okay?
Now it's okay. Now it's okay.
Okay. So someone was saying that B is correct, but okay. B- Forget about f prime k being a pseudo random permutation. It's not even a permutation because as we saw over here, for x1 and x2, that's for both 1 and 2, the value of f prime k is the same. So it's not even a permutation. So B cannot be true. Now C is true because, well, okay, to instantiate OFB mode of operation, we need a secure PRF, right? But in A, we proved that f prime k is not a secure PRF. So we cannot use f prime k to instantiate the OFB mode of operation. And similarly to instantiate the CTR mode of operation, we also need a secure PRF. But since f prime k is not a secure PRF, we can't use it to instantiate the CTR mode of operation either, right? So is this fine? Oh yeah, yeah. So here we are supposed to pick the correct ones. Yeah, but yeah, B and D
Sir,
are incorrect. Yeah.
sir, I have a doubt on the second probability. The probability
Okay.
of B that's equal to 1 given B equal to 0. Can you please explain that?
Okay. So okay, when B equals to zero, what's the verifier going to do? It's going to play with a totally random function, right? So, and what property do we have for a totally random function? The value of a totally random function at xi is number one random and number two independent of the value of the function at any other point, right? So, uh, b prime equals to 1 given b equals to 0 means that y1 equals to y2 when b equals to 0, which is y1 equals to y2 when both are independent and random. Why? Because when b equals to 0, the verifier is playing with a totally random function, and so like its evaluations at two different points would be independent and random, right? So is this equality clear to you?
No, sir.
Okay. So when b equals to 0, we have a TRF, right? A totally random function. Okay.
Yes, sir.
Now let's say you have a totally random function and you evaluate it at 2 points. Uh, and let's say the value of the now what relationship do you have between the values at those 2 points? They are independent and random of each other, right? This is the definition of a TRF. Okay. So when is b prime going to be 1? B prime is going to be 1 if y1 equals to y2, right? Now what is y1? It is a totally random function at x1 and y2 is a totally random function at x2, right? Now x1 and x2 are distinct. So uh, y1 and y okay, so the b prime equals to 1 means y1 equals to y2. But since we are playing with a TRF, we have y1 equals to y2 when uh, both y1 and y2 are independent and total, and totally random strings, right? So is this fine now?
सर आपकी वॉइस ना बहुत ब्रेक कर रही है।
Okay, is it breaking for others as well? Am I audible?
अभी ठीक है सर।
Okay, so was my voice breaking for others as well? Okay, okay, so let me try to which one is my different network. Yeah, can you hear me? Okay, can you? Okay, yeah. So I've changed my network. Let's see if this is better. Okay, so yeah. Okay, let me go over this equality again. So when is B prime? First of all, when B equals to 0, phi1 is the evaluation of a totally random function at x1, and y2 is the evaluation of a totally random function at x2. Now, since x1 and x2 are different strings, y1 and y2 are going to be independent and random. Okay, this is just the definition of a totally random function. So is this fine?
यस सर।
Okay. Now, when can B prime be 1? Okay, look at what the distinguisher does. So B prime is 1 when y1 equals to y2. Okay. So when B is 0, we have this part. Y1 and y2 are independent and random. And B prime equals to 1 just means y1 equals to y2. So is this equality fine now?
यस सर। लिटिल मतलब अभी भी डाउट है, पता नहीं, समझ ही नहीं
Okay,
आ
so
रहा
like,
थोड़ा।
okay, what is it that you don't understand?
Why is the probability 1 upon 2 raised to power n?
Okay, we like till now I've just explained this. Is this equality clear? Not about this. I'll come to this later. Okay. Is just
It's
this
fine.
part clear?
Yeah. Yes, yes.
Okay. So now okay, fix y1 to be any string you want. Okay. What is the probability that y2 would be equals to y1? Then y2 is independent of y1 and completely random. So let's say y1 is 0 to the n. What is the probability that y2 is also 0 to the n?
1 raised to 1 upon 2 raised to power n, na?
Right. So that's exactly this, right? And this is true for any value of y1, right?
Yes.
Right. So is it fine now?
Yes, sir.
Okay, yeah. So this is fine. Let's move on to the next problem. Okay, yeah. So the next problem is let f be a function from 0 comma 1 to the n times 0 comma 1 to the n to 0 comma 1 to the n. And suppose that f is a secure PRF. Then which of the following constructions is or are secure PRF? The first option is f prime, which is from 0 comma 1 to the n cross 0 comma 1 to the 2n to 0 comma 1 to the n, and is defined as f prime k of x concatenated with y equals to the XOR of fk of x and fk of y. Option B is f prime is now from 0 comma 1 to the n to cross 0 comma 1 to the 2n to 0 comma 1 to the 2n, where f prime k of x concatenated with y is defined as fk of x concatenated with fk of y. The third option is f prime is again like the first option from 0 comma 1 to the n cross 0 comma 1 to the 2n to 0 comma 1 to the n, and f prime k of x concatenated with y is the and of fk of x and fk of y. Option D is it's from 0 comma 1 to the n cross 0 comma 1 to the n to 0 comma 1 to the 2n, where f prime k of x is fk of x concatenated with fk of x concatenated with 1, and option E is none of the above. So which of these are secure PRFs? Okay, so you are saying that one is a secure PRF. Okay, why do you think one is a secure PRF? One and three are secure PRFs. Okay, so why do you think that one is a secure PRF? Okay, right. So let's say, okay, so right. Yeah, you are right. XOR operations leads to more random strings. But what's the definition of a TRF? For a TRF, you not only need the strings to be random, you also need them to be independent of each other, right? So over here, f prime k has what we can show is that f prime k has one property of TRF, that is the outputs look random, but we also need to be able to argue that the outputs also look independent, right? So suppose I pick x and y and some other x prime and y prime, then what I should be able to argue is that f prime k of x concatenated with y and f prime k of x prime concatenated with y prime, these two should be independent, right? So do you get my point? Do you get why just saying that XOR operation gives you random strings does not prove that f prime is a PRF? Yeah, so if this question were about PRG, what you argued would be correct. Yeah, so actually over here, none of these are secure PRFs, and let's see why. A lot of these would give you random strings, but they won't give you independent random strings. And yeah, the independence plays a crucial role over here. So how much space? Okay, yeah, so let's see why each one of these is not a secure PRF. Okay, so let's start with A. Okay, so again, we'll just create a distinguisher for A. So what a distinguisher will do is the following. It will send two pairs, x1, y1. Here, x1 and y1 can be anything. And okay, wait, I want to use y for output, so let me use x1, x2. So it's going to send these two queries to the verifier, x1 concatenated with x2. And yeah, I want to call this one. It's going to send x1, which is x11 concatenated with x12, and x2, which is x21 concatenated with x22. As usual, the verifier would, yeah, toss a coin. If it's zero, pi I is TRF of xi I in 1 comma 2. And if p equals 1, it's going to pick a key uniformly at random from 0 comma 1 to the n. Set yi equals to fk of x1 XORed with fk of x2, and then it's going to send y1 and y2 to be t. Now what t will do is it will check this. If yes, set b prime to 1, else set b prime to 0 and return b prime. Okay, so it's clear that D is an efficient algorithm. So now let's see why it's able to like distinguish between this function f prime and the TRF. So let's look at this probability. So when B equals to 1, what's y1 going to be? Y1 is going to be, yeah, okay, so yeah, let me put, write it down better. So y1 is going to be fk of, yeah, this should be xi1, xi2 over here. So y1 is going to be x11 XOR fk of x12 and y2 is going to be fk of x21 and x2. Now what the adversary can do is the following: set x21 to x12 and x22 to x11. In this case, this is just going to be fk of x 12 k of x11. So in this case, y1 and y2 would exactly be the same. So this probability would just be 1. And for this probability, so again, probability, it's the same thing as above. So I can just copy paste it. Yeah. Okay. So again, when b equals to 0, uh, we are going to have a totally random function. Okay. And when we have a totally random function, what's the probability that y1 and y2 would be the same? Well, again, it's this time it's 2 to the 2n because now, oh wait, no, it's just 2 to the n because the outputs are still n with strings. Yeah. So when we have a totally random function, y1 and y2 are going to be independent and random, and so the probability that they are equal is just 1 over 2 to the n, as we saw before, right? So again, even in this case, there is a the difference between these two probabilities is 1 minus 1 over 2 to the n, which is non-negligible. So we have created a distinguisher for this function. So this can't be a PRF. And over here, we crucially use the fact that the when it's using a TRF, the outputs of the queries are random and independent. But when it's using a PRF, while the outputs to the queries are close to random, they are not independent, right? That's what we used over here to show that y1 and y2 are the same. So is this fine? Because I think all four have something similar, independent swings somewhere. Okay, so if this is fine, let's look at option B. It's just a concatenation. Yeah, so most of the things are usually applicable. Your parents
Sir,
were, yeah,
sir, in this matlab, if we have to show it is secure, matlab anything secure or insecure, just we need to find the distinguisher only ना. The probability will always be non negligible, मतलब वो non negligible आ ही जाएगी वो तो, मतलब जैसे
that, okay, so, no, but okay, so even while creating the distinguisher, you should have the probability in mind, right? Like, if you create a distinguisher properly, then yes, you would always get a non-negligible probability.
क्योंकि हमें उससे तो कोई मतलब ही नहीं है ना, जैसे 1/2 n जो बन रहा है उससे तो
Hmm.
हमें कोई, वो तो कुछ ना कुछ आएगा ही, वो प्रोबेबिलिटी ना वो वाली हमें डिस्टिंग्विश करने का,
Right.
वो 1 बन रहा है हमारा, वो
Okay,
इम्पोर्टेंट
okay,
है।
fine, fine. No, no, no. What if this is one and this is also one?
ओके ओके।
Right. So you would have to find both of these, but you are right. In most examples or most problems that you would encounter, if this is one, this is going to be something like half or 1/2 TN or something like that. This is
ये तो
always
वन
going to be,
कभी आ ही नहीं सकता मेरे को लगता है, इट कैन नॉट बी।
you are right. Yeah, but at least, but you would still have to find this out every time. Because sometimes what can happen is this can be half and this can be pretty close to half. I think in the last few classes we did see something like that. So, okay, it's fine if you don't find this out exactly, but just argue that this is negligible or this is significantly away from one.
ओके सर, आई अंडरस्टूड।
Yeah. Okay, so what was the second thing? Okay, yeah, in second thing, we're just concatenating the two goods. So over here, yeah. So over here, it's just going to send x1, which is 0 to the n concatenated with 1 to the n, x2, 0 to the, no, yes, 1 to the n, 0 to the n. On what intuition we will take as options. Okay, right. So, mm, okay, so over here, the in option A, the observation was this. It doesn't matter. Okay, so XOR is a symmetric operation, right? So it doesn't matter whether you switch X and Y or not, right? So this tells you that so like this tells you that by like you should just switch because in that way you would get a different someone was like yeah. So yeah, so if you just switch, you would get a different point, but you would still get the same function value. So, okay, so when you have a candidate PRF or a candidate PRG in mind, first try to reason about how, first try to intuitively reason about how close it is it to a totally random function or a truly random string. From that intuition, you would get some idea of what you should be trying to prove, whether it is a PRF or a PRG or whether it is not a PRF or a PRG. And once you try to make some comparison like this, you would at least have some candidate strings in mind, and then you can just try them out. Yeah, that is like there is no okay, there is no algorithm that would always give you the strings, if that's what you ask. Okay, hit and trial, but okay, so it would really help if you had some intuition about this beforehand. For example, for option A, you had this intuition, right? That okay, XOR gives you random strings, right? And that intuition would have worked for PRG. So if you wanted to show that this was a PRG, you could have done it using just that intuition. But over here, the when you over here, your intuition should have been okay. Are they random and are they independent? The moment you ask about are the moment you ask the question, are they independent? You realize that if I switch x and y, the value of the function is going to be exactly the same, and that gives you a candidate value of X and a candidate value of Y, right? So it's some sort of hit and trial, but it's not completely random. Yeah, there is some method to it. Okay, so hmm, okay, yeah. Okay, so we were looking at the option B. In option B, it's f prime kxy is just fk concatenated with fy, fky. Okay, so over here as well. Okay, observe that if I switch the places of x and y, what will happen is that these two will switch places, but the two, okay, so the two strings would just be like, the two strings would almost be the same, that just the blocks would be swapped. So this again gives you an intuition of what you should be using. So over here, we are just swapping x and y, and we'll get like, we'll hope to get two strings whose blocks, if you swap the two blocks, they give you the same string if a PRF, a PRG is being, PRF is being used. That's okay. Now I'll just copy this part here. Okay, yeah. So again, it will toss the coin. If it's zero, it's going to use a TRF. If it's one, it's going to use a PRF. But in this case, it's going to be y equals to fk of x I1 concatenated with fk of x I2. So yeah, this is x11, x12, x21, and x2. Then it's going to send y1 and y2. And now what we'll check is the following. Let yi be yi1 concatenated with yi2. And what we are going to check is this, is y11 equals to y22 and y22 equals to y out the same thing. Y21 equals to y12. If yes, set b prime to 1. No, set b prime to 0. Yeah, you send back b prime. Okay, so yeah, again, this probability is going to be the same. Okay, so in the case when uh, b is 1, we are going to be using f prime. So y1 is going to be this 0 to the n concatenated with 1 to the n, and y2 is going to be 1 to the n concatenated with 0 to the n. So in this case, the check always passes because y11 equals to y22 and y21 equals to y12, right? So this probability is 1. And yeah, the other case. So again, the probability is going to be very negligible. So this is going to be 1 over 2 to the n times 1 over 2 to the n, which is 1 over 2 to the 2n. Why? Because y1 and sorry, like all these are n bit strings. So the probability that these two are going to be the same is going to be 1 over 2 to the n. And these two being same would also be 1 over 2 to the n. So it's 1 over 2 to the 2n. So again, this difference is large. And so this function can also not be a PRF. So is this fine? Okay, so let's look at option C. Okay, so in C, what we are doing is f prime k of x concatenated with y is equal to fk of x and fk of y. Okay, so
सर
uh,
एक
yeah,
डाउट है मेरा, एक डाउट है सर,
uh,
जैसे ना प्रोबेबिलिटी हम निकाल रहे हैं जैसे, तो वो जैसे वन ही है वहां पे, तो हमने एग्जैक्टली फाइंड आउट कर दिया कि वही
hmm,
आएगा, है ना? तो बट
hmm,
अगर वहां पे ना कुछ भी होगा अदर देन 1 टू पावर 2n, तो वो नॉन नेग्लिजिबल ही आएगा ना, मतलब।
okay, okay. So as long as this is ये जो probability है ना, as long as this is 1 over pn, you would be fine.
ओके, बट ये पी की पावर n तो नहीं है, ये तो पी मतलब कांस्टेंट कोई।
नहीं, okay, नहीं, नहीं. 1 over inverse poly. Okay, let me write it. 1 - 1 over p of n, where p is a
ओके
polynomial.
ओके,
Right.
ओके ओके, मतलब
Yeah.
पॉलिनॉमियल होगा तो मतलब तब
तब
हमें,
दिक्कत आएगी.
हाँ तो दिक्कत आएगी, मतलब ऐसा नहीं
Right.
होना चाहिए फिर तो, मतलब हार्ड
Exactly.
है, फिर भी हार्ड है
Yes.
मतलब।
But in most of these problems, yeah, this would either be something like 1 over 2 to the n or 1 over 2. But yeah, it's still at least okay. If you don't want to find it out exactly, just estimate it. An estimate would be good enough. Okay, so yeah. So option C was f prime k x concatenated with y equals to fkx and fky. So now in this case, what you can do is you you can uh, suggest which strings we should use as for x1 and x2. Okay, this is similar to what the first two parts. So yeah, try suggesting what we should use for x1 and x2. Okay, so this is very similar to the first part, right? Because even if I switch the places of x and y, so when I switch the places of x and y, these would be different, but this would still be the same, right? So again, we can do something like what we did in the first part, right? So over here also we can do something like, let's say, x11 and x12 and x21 x22, लेकिन x21 is just x12 and this is just x1. The rest is going to be the same as 1, so I'll just copy it. Yeah, yeah, just this part would differ. So if uh, for probability b prime equals to 1 given b equals to 1, instead of x or we now have and, same over here. Yeah, but both x or and are like they have the same property, right? That they are symmetric, so it doesn't matter whether you compute a and b or b and a, they are going to be the same. So again, the rest of the analysis is just like one. All you have to notice is that we can use the same strings that we used in one. So is this fine?
यस सर।
Okay, so in that case, let's look at D. Okay, what was D? Okay, so it's f prime k of x is fkx concatenated with fk x concatenated with 1. Wait, wait, there should be n plus 1 in that case. Okay, this should be plus 1 over here because otherwise over here you should have n plus 1. Yeah, this should be plus 1. So again, over here, the addition. So like to add, I will just treat both. We will treat x as a number and addition would be modulo like 2 to the n. So over here, like this is also similar to b. So would you like to guess what the strings are going to be? Okay, so here's one thing that we can do. X2 is 0 to the n minus 1 and 1. So this is x1 as a number is 0, x2 as a number is 1. Yeah, mostly copy paste. So yeah, again, this part is going to be the same, just this will, oh, I should change it over here. So when b equals to 1, we are going to be playing with this function f prime k. So yi would be xi concatenated with fk of xi plus 1. And okay, now the check would slightly change. Okay, so now let's look at this probability. Probability b prime equals to 1 given b equals to 1. Okay, so in this case, what's y1 going to be? In this case, y1 would be fk of 0 to the n concatenated with fk of 0 to the n plus 1. So that's fk of 0 to the n minus 1 time 1, right? And what about y2? Y2 would be minus 1, 1. This is x2 concatenated with fk of 0 to the n minus 2, 1, 0. Since x2 is 1, when I add 1 to it, I get 2. So this is what I'll get. Now, okay, again, notice over here that like whenever b is 1, this and this are going to be the same. So since that's the check they are performing, this is y1, 2, and this is y2, 1. This check will always pass. This is always 1. And again, when b is 0, both of these strings are going to be independent and random. So the probability that these two, which are strings of length n, independent and random, the probability that they would be the same is 1 over 2 to the n. So again, this difference is large. So again, this also can't be a PRF. Is this fine?
Yes, sir.
Okay. Yeah. So in that case, let's move on to the next problem. Okay, so this problem is about one-way functions. So can anyone of you recall what one-way function is?
सर मेरा एक डाउट और है कि
Hmm?
सर ना ये जैसे सिक्योर कैसे बोलेंगे हम, मतलब सिक्योर तो है ही नहीं, फिर मतलब सिक्योर के एग्जांपल है आपके पास सिक्योर ये?
Okay, that's a good question. Okay, so we don't have any provable, like we don't have any PRFs which we can show are provably secure. So that's okay. So you saw in class, right? That so in class you saw theoretical construction of a PRF and a practical construction and some practical constructions of PRF, right? Now the reason we saw practical constructions of PRF is because we do not know how to theoretically construct PRFs, right? So as of now, we do not know of any function which we can prove is a PRF. But
ओके,
we
तो
have,
मतलब
yeah.
अटैक आ ही जाते हैं, मतलब कोई ना कोई अटैक कर ही देता है कुछ ना
Oh, no,
कुछ
no, no, no.
ऐसे।
For example, as of now, we don't know of any attacks against AES, right? But we can't prove that AES satisfies this definition, this indistinguishable base definition. What we have observed empirically is that AES is appears to be secure, but we can't prove that AES is secure.
ओके।
Okay, one way to think of it is like, so far we haven't gotten any attacks against AES, but we can't, can't be sure that in future we won't get any attacks against AES because we haven't proved that it satisfies this definition. So, does that answer your question?
ये सर, तो सर ऐसे तो ना कोई भी स्कीम बना सकते हैं एईएस के कुछ भी मतलब बना सकते हैं कोई भी, तो
Right,
बोलेंगे
you
कि
can, but then someone might come up with an attack, right?
ओके ओके।
Right. So the good thing about AES is so far it has stood the test of time. So far we don't have good attacks against it, right?
ओके ओके।
Yeah. Yeah. Someone had written in chat what one-way function is. It is one-to-one functions which are not invertible and are deterministic, right? Okay, right. So one-way function is basically a function which you, okay, so it's f is said to be 1, 1. If you can compute f efficiently, but you cannot compute f inverse efficiently. Okay. So the question is this. Let f be a one-way function. Yeah, invertible, not convertible. Yeah. Then is g defined as g is equal to f of x also a one-way function? So is the question clear? We are assuming that we have one-way function f, and we are asking if f composed with itself is also a one-way function. So what would be your intuition? If f is difficult to invert, should f of f also be difficult to invert? Because if I can invert f of, okay, right. So because, okay, so if, okay, so here's the intuition. If I can invert f of x, then here's the way to invert f. Apply f to it. So given f of x, compute f of x, and then we'll invert f of x, right? That would give you an x prime. Okay. But the problem with this is the following. We are assuming in what I just said, we were assuming that f of x equals to f of x prime implies x equals to x prime. So this is what we were assuming in what I just argued. The problem is this might not be true. So, okay, let me tell you the answer to this is no. Just because f is a one-way function, f of x need not be a one-way function. And here's a neat construction of that. Okay, so, yeah, okay, yeah. So, let f prime be any one-way function from 0, comma 1 to the n over 2 to 0, comma 1 to the n over 2. Define f of x as, okay, define f of x1, which is a string of length n over 2, concatenated with f of x2, which is x2, which is also a string of length n over 2, as f of x2, 0 to the n. It can be shown. So I won't formally show that f is a one-way function because we have done something similar in class. Oh wait, this should be f prime. Yeah. So you can try showing on your own that if f prime is a one-way function, that f is also a one-way function. If you can't, then ask me in the next lecture or in the forums. So yeah, I won't show that f is a one-way function, but yeah, we can prove that it's a one-way function. Now what we're going to show is that f of x is not a one-way function. Okay. So the claim is this: for any x in 0, comma 1 to the n, what is f of x? So f of x, let's say x equals to x1 concatenated with x2. So f of x equals to f of f prime x2 concatenated with 0 to the n over 2, right? Over here, this part now plays the role of x1 and this part plays the role of x2, right? So what's this going to be? This is just going to be f of f prime of x2, but x2 over here is 0 to the n over 2, 0 to the n over 2. Now this is true regardless of what value of x I pick, right? So uh, for all x, f of x is just a fixed string where all x are its primitives. This. So over here, someone was showing, yeah. So over here, f of x is very easy to invert because its range is just one. So so we are only going to be ever asked to invert like f of x at one point, and we can output any string of length 0 to the n. Sorry, any string in 0, comma 1 to the n, and we would be fine. Yeah. Someone had a question. You can either unmute yourself and ask or put it in the chat. Okay. Okay. So, like, yeah, if you have a question, you can either put it in the chat or just unmute yourself and ask. Okay. So, yeah, is this clear why we can like easily compute the inverse of f of x? Because what's happening is this. Mm, This is the domain of f. It's sort of mapping to a, so whole of f is mapping to this part, and whole of this part is just mapping to one string. So the image is like anything over here. So is this clear? Should I go over this again?
Mm,
Like, did anyone have a question? Okay, yeah. Okay, so we have a one-way function f, and so it's defined like this. And now what we're going to show is that no matter what x you pick, f of x is just going to have one value. Okay. So what's f of x? It's f of f prime x2 concatenated with 0 to the n. Now this is going to play the role of x2. So it's f prime 0 to the n over 2 concatenated with 0 to the n over 2. Okay. Now if you recall, in that one-way function game, what's happening? You verify your distinguisher. The verifier picks an x at random and sends, in our case, f of x to the distinguisher, right? And what is the distinguisher supposed to do? That the distinguisher is supposed to output x prime such that f of x is equal to f of x prime, right? So this is the goal of the distinguisher. What I'm claiming is that in this case, this goal is very easy to achieve because all the distinguisher has to do is to set this to be 0 to the n. Why? Because no matter what string you put in place of x prime, you're always going to get this y concatenated with 0 to the n, right? Yeah, so over here it doesn't matter, like, yeah, it doesn't matter what you output, you're always going to be correct. And the reason like this is working out is because that property that we saw, right? Uh, we made this assumption, right, while arguing intuitively that f of x equals to f of x prime implies x equals to x prime. This isn't true in this case. That's why this is failing. Now, let's look at a similar problem. So in this problem, the setting is just the same as the previous question. But now f is not just a one-way function, it's also a permutation. So the question is g a one-way function now?
Yes, it will be, I think.
Right. Why? Because that property that I just wrote and read would work now. So yeah, yes, because suppose f of x1 is equal to f of x2, since f is a permutation, f of x1 is equal to f of x2. In fact, so if there exists a PPT distinguisher, rather PPT adversary, we are not in the PRF file. So if you have a PPT adversary D, which can output x prime such that f of x prime is equal to f of x, or a random x sent by the verifier or the challenger. And we also have that is inverting f of this also, also means inverting. Okay, so yeah, one-way function is okay. So okay, are you asking about one-way function or a one-way permutation? Because like permutations have to be one-to-one, right? Okay, so okay, okay. A one-way permutation would be so a one-way permutation would be 1 to 1, easy to compute and difficult to invert. But as you said, you can still invert it correctly with negligible probability. Yeah, but since it's a permutation, it has to be 1 to 1.
Sir, is there any one-way permutation available? Matlab, you know.
Okay, so if you have one-way functions, okay, a one-way permutation is a one-way function. If you have a one-way function with a hardcore predicate, we saw that you can construct a PRG. If you have a PRG, we saw you can construct a PRF, right? But as we discussed before, we don't know how to construct PRFs. Like we don't know how to construct functions which we can prove are PRFs. We also don't know how to construct functions which are one way.
It seems very difficult ना मतलब अगर
Right.
one one want to
Okay.
invert नहीं हो रहा yeah.
Right. Basically, constructing one way functions is okay. So it is okay. Constructing one way functions is in some sense at least as hard as proving that P naught equals NP. Because what is a one way function, right? It's difficult to invert, but so if you show that something is difficult to invert, you've already shown that there is a problem which is hard, right? That would in some sense imply P naught equals NP. So yeah, right now we do not know of any theoretical construction of a one-way function. Any construction that we can prove is difficult to invert, but we do have some candidates. For example, factoring is one such prime factoring is one such candidate. So the function is this: I give you two. Let's say I give you a bunch of primes. You multiply them. That's your output. But given a number, it's difficult to find its prime factors. So this is a candidate one-way function. As you'll see in the second later part of the course, we have we have even built some crypto systems based on this one way, like this function. But we can't prove that it's a one way function. So does it answer your question?
Yes sir.
Yeah. Okay, so how much do we have? I think okay, yeah, we can solve this and then we move to the next part. Okay, so the next question is about PRPs and SPRPs. So assume that PRPs exist, then can there exist a PRP which is not an SPRP? So, do you recall what an SPRP is? Okay, so in that case, let's do one thing. Let's skip this question because if I have to define SPRP, that would take some time. So let's skip this question. If you have time, we can come back to this later. Yeah. Okay, so let's. I think this is the last question for from week 4. Yeah, then we can move to week 5. Okay, why is this? Yeah. Okay, so let's look at this. Suppose that while transmitting the ciphertext blocks C1 to CT, the ith block is dropped. That is, for some reason, the ith block did not get transmitted. So the ciphertext that the receiver received was just C1, C2 to Ci minus 1, Ci plus 1 to Ct. Okay, so the ith block is missing over here. Then be the effect on the decrypted message blocks if we are using the CBC mode of encryption, the OFP mode of encryption, and the CTR mode of encryption? So is the question clear, or should I explain the question again? So basically, the receiver got only some blocks. One block was missing. It's going to try to decrypt all the blocks. What would how many of these blocks would decrypt correctly? That's the question in these three modes. And we saw something like this in the previous session, but that over there we were just missing a bit. Now we are missing an entire block. Yeah, so you are right. C1 to Ci minus 1 would decrypt correctly. But yeah, the problem is with the later blocks. Okay, so let's assume that suppose the blocks are m prime 1, m prime 2 to m prime t minus 1. T minus 1 because since one ciphertext block is missing, there is no way we are going to be able to recover M1, right? Sorry, MI, right? So the best we can hope for is to recover all the other blocks correctly. So let this be our decrypted message. And since C1 to Ci minus 1 are received correctly, M prime 1 is going to be M1, M prime 2 is going to be M2, and so on up to M prime I minus 1 is going to be Mi minus 1 in all modes of operation. Okay, so now let's look at what, okay, also we won't be able to recover the MIS block because Ci is blocked. So now let's just look at what happens to the other blocks, Mi plus 1 and so on. Okay, so yeah, first let's look at the CBC mode of encryption. So what's M prime I going to be? It's going to be C prime I XOR with Fk of C prime I minus 1. So here what I'm doing is I'm calling C1 to Ci minus 1, Ci plus 1 to Ct. So these are C1 prime to Ci minus 1 prime. This is Ci prime and this is C prime T minus 1. Because as far as the receiver is concerned, this block is the ith block. It doesn't know that a block has been, that a block is missing. Yeah. So M prime I is going to be this, and this is C prime I, it's C I plus 1 XOR with, oh yeah, sorry, yeah, it's thanks for that. Okay, what's C prime I minus 1? C prime I minus 1 is Ci minus 1. Now, in the best case, what can we hope? We can hope that M prime I is Mi plus 1, right? It can't be Mi because Mi is lost. In the best case, we can hope that M prime I is Mi plus 1, M prime I plus 1 is Mi plus 2, and so on. But for Mi plus 1, we need this. So this is not going to be Mi plus 1. So we won't be able to recover the I plus 1th block either when using the CBC mode of encryption. So Mi plus 1 can also not be recovered. What about the later blocks? Turns out they can be recovered. So what's M prime I plus 1 going to be? It's going to be C prime I plus 1. XOR with Fk inverse C prime I. Okay, now what's C prime I plus 1? It's C of I plus 2. And what's C prime I? It's, so this is exactly equals to Mi plus 2. So what's going to happen is the following. M prime I plus j is going to be M of I plus j plus 1. So we, when using the CBC mode, we are able to recover the blocks M1 to Mi minus 1 completely. There is no hope for Mi, so forget about that. Mi plus 1 won't be recovered correctly, but all the other blocks would be recovered correctly. So if one block is dropped, we would only be missing out on one block in the output that the receiver can decrypt. Okay, is this fine? Okay, so which part didn't you understand? Okay, yeah, you're still right. Okay, yeah. So what's M prime I plus 1? Okay, how would the receiver compute M prime I plus 1? The receiver would compute M prime I plus 1 is C prime I plus 1 XOR with Fk inverse C prime I. Okay. Now what is C prime I plus 1? Uh, C prime I plus 1 would be, so C prime I is Ci plus 1. So C prime I plus 1 would be Ci plus 2. Okay. And C prime I is just Ci plus 1. So M prime I plus 1 would be Ci plus 2 XOR with Fk inverse Ci plus 1, right? But this thing is just Mi plus 2, right? So at least, do you see that M prime I plus 1 would be Mi plus 2? That is, we would be able to recover Mi plus 2 correctly. So, yeah. And okay, what about the other blocks? What would happen is over here, instead of I, you would have J. So over here, you would have J. Over here, you would have J. Basically, everywhere over here, you would, like, okay, so let's say over here, you had 2. Then over here, you would have 2. Over here, you would have 2. Basically, what is happening is the following. Every block depends on just two blocks. So M prime I just depends on C prime I and C prime I minus 1. So as long as you are sufficiently away from the block that you drop, you should be fine. Okay. So this is what happens in the CBC mode. Okay, let me get a picture. Now what happens in the OFB mode and the CTR mode is almost is similar. So let me not work out the OFB mode. Let me just work out the CTR mode. This is much cleaner. So in the CTR mode, what we would have received, we would have received C1, the initial counters, Ci minus 1, Ci, and Ci plus 1 and C2. Let's just call this C0 prime, C1 prime, Ci minus 1 prime, Ci prime, and so on up to C prime T minus 1 because we dropped one block. Okay, so again, as before, M1 to Mi minus 1 would be recovered correctly. There is no hope to recover Mi. So let's forget about that. What about the next block? So what would the receiver do? The receiver would do M prime I is equal to uh, Ci or C prime I XOR with Fk C0 prime, which is the counter, the initial counter, plus I, right? But this is Ci plus 1 XOR with Fk counter because both of these are counters. the same counter CTR plus I. Now this is not equals to Ci and it's also not equals to Ci plus 1, right? So we aren't able to recover Mi plus. And similarly, we also won't be able to recover Mi plus 2 and so on. Now, let me just give you one example. I plus 1. This is equals to Ci plus 2 CTR plus I plus 1. But this is neither Ci plus 1 nor is it Ci plus 2. So what will end up happening is like you can do this for anything, and you would get that for all j greater than equals to 1, Mi plus j can't be recovered. So is this fine, or should I also explain this part again? So what is basically happening over here is the following. If you look at this equation, over here it's important for us to get the exact block number, right? But if you are missing a few blocks, this block number is always going to be incorrect. And so everything after the dot block is going to be messed up. It is in the wrong order, right? And the same thing would happen with the OFP mode as well. So in these two modes, even one drop block is going to mess up all the blocks after that. Is this fine? Yeah. Okay. So if this is fine, let's move on to problems based on week 5's content. So the first problem from week 5 is the following. So consider a MAC construction for messages of length 2n using a secure PRFF. Now, to authenticate a 2n-bit message, m equals to m1 concatenated with m2, both m1 and m2 have size n. They are going to output the tag fkm1, fkm2, randomly picked key k. So select the incorrect options. This MAC is CMA secure. This MAC is SCMA secure. The tag generation algorithm is deterministic, and the tag generation algorithm is randomized. So would you like to guess like which of these are correct? Oh, sorry, which of these are incorrect? Okay, let's forget about CMA security and SCMA security for now. Oh yeah, almost in CPC we won't be able to decrypt CI and CI plus one, right? Because CI plus one also depends on CI. So the only two blocks depending on CI are CI itself and CI plus one. So you won't be able to decrypt them, but you'd be able to decrypt everything else. And in the other two modes, you won't be able to decrypt CI and anything after that. Yeah. Okay. Yeah. Yeah. So in this question, okay, let's forget
Can
about
you
yeah.
can you please मतलब एक बारी वो बता देंगे सीएमए और एससीएमए में क्या डिफरेंस था? और सिक्योर मतलब एक
Okay.
रैंडमाइज़ था कुछ था मेरे को याद नहीं है ढंग से।
Okay. Right. So in CMA security, what's happened? Okay. What in CMA security, what is going to happen is the distinguisher is okay. Yeah. Let me just write it. It will be easier that way. So in both cases, there is a verifier, there is a distinguisher, or okay, no, an adversary. So what an adversary would do is it would send a few messages to the verifier. And the verifier would send the corresponding tags to the bad choice. And the verifier would send the tags to the adversary, right? Now the adversary is supposed to find a pair M star, comma T star, such that T star is a valid tag for M star. Okay, now here's the difference between CMA and SCMA. In CMA, you have ML, and in SCMA, M star, comma T star. The difference between CMA and SCMA is the following. In CMA, you should be able to produce a message. So you should be able to forge a tag for a new message. Okay. And in SCMA, you are allowed to forge a tag the for one of the messages M1 to ML. But let's say you forge a tag for M1, that tag has to be different from T1. In CMA, so let's say you are playing the CMA game and you forge a tag for M1, the tag is different from T1, you still don't win the game. In SCMA, you do win that game. So is the difference clear now?
मतलब in CMA the tag can be cannot it cannot be no, it can be deterministic na,
Right.
but
So
in
CMA,
SCMA.
right. CMA captures deterministic max. SCMA captures randomized max. So does this clear the CMA versus SCMA confusion?
Yes sir.
Okay, so yeah. So let's look at the option. The construction is CMA secure. It's SCMA secure. The tag generation algorithm is deterministic, and the tag generation algorithm is randomized. So okay, let's first forget about CMA, SCMA. Which of C and D is correct? So this is the tag generation algorithm. Is it randomized or is it deterministic?
Deterministic.
Why?
We are using na FK pseudo random function.
Right. Okay, so okay, there is randomness over here, K, but that would come from the key generation algorithm, right? Not of the tag generation algorithm. So tag generation algorithm just takes K as input, takes F as input, takes M1 and M2 as input, and out does some deterministic computation to output this. So yeah, you are right. Uh, in okay, so we are supposed to select the incorrect option, so this is incorrect. And what about security? Like, is this CMS secure? Is this SCMS secure? Is it or is this not secure at all? Would you like to take a guess? Okay, so it's neither
ओके ओके सर
CMS.
इसमें
Yeah,
हाँ ओके
नहीं बोलो.
नहीं नहीं ये मैं यही बोल रहा था अगर ये डिटर्मिनिस्टिक है तो ये सीएम में ही हो सकती है बाकी तो एससी में
Right,
नहीं हो सकती
right. But this, yeah, but this is not even CMS secure because like we can create an adversary that can forge the tag. Okay, so let's see how to. Okay, out of space. So let's create an adversary that can forge the tag. Okay, so there is a verifier and a distinguisher. Adversary with a distinguisher. And what's the adversary going to do? It's going to what am I using? M1 into. So it's going to send two messages. M1, which is Am I using concatenation? Yeah, concatenation. So M1 would just be, let's say, 0 to the n, 1 to the n. M2 would be, let's say, okay, let's say M1 is x1, x2, and M2 is x3, x. Now this will return tags T1 and T2. Let T1 be T11 concatenated with T12, T2 be T21 concatenated with T22. What the adversary will do is the following. It's going to put x1, x3. So this is a new message, and the tag is wait, T11 concatenated with T21. Yeah. Okay, so this is what the adversary is going to do. Now, the adversary is clearly efficient. Now let's see if the tag is valid or not. Okay. So first of all, this message x1 concatenated with x3 is different from this message as long as, yeah, let's just assume that x1 is not equals to x2 is not equals to x3 is not equals to x4. So as long as this is satisfied, this message is different from this message as well as this message, right? So, but what will T1 be? Since T1 is a valid tag for M1, T1 is just fk x1 concatenated with fk x2. Similarly, since T2 is a tag for M2, T2 is fk x3 concatenated with fk x4. Okay, and now we want to forge a tag for x1, x3, right? Tag for x1, x3 looks like fk of x1 concatenated with fk of x3, right? Now, okay, this is T11, this is T12, this is T21, this is T22, right? So the tag should look like uh, T11 concatenated with T21, right? But that is exactly what the adversary was able to output over here. So the adversary is able to forge a tag for a new message, right? So this scheme is not CMS secure, and as you said, it's not SMS secure, CMS secure either, right? So is this clear?
ये सर अगर ये पूरा एक ही उससे होता है एफ के एक्स वन ही रहता मतलब एक ही वो रहता तब नहीं कर पाते शायद डिस्टिंग्विश ना सर
Right. So yeah, that is how we constructed the Mac in class, right? So like when we have just one message, let's say yeah. So let's say
इसमें
this wasn't there and this wasn't there. Then we wouldn't have been able to
हाँ हाँ
distinguish, right? So this is how we constructed the Mac in class. So this is an interesting question. Suppose pi, key generation, and tag verification is a secure Mac for n-bit messages. Then and suppose a tag generation algorithm outputs a tag of length tn. How large should tn be? Small omega of 1, small omega of log n, small omega of n, or nothing can be said about tn. So just from the fact that this scheme, sorry, this Mac is secure, let's say CMS secure, Can we say anything about how large the input of text generation can be? So would you like to guess which of these is the answer?
N omega n. It should be.
Okay, omega n is a bit too much. It's omega log n. Okay, here's the reason why. Suppose it were, suppose that Tn were, let's say, order log n, right? Then what an adversely can do is the following. For a message, M is for M by just randomly picking a string, a string T. Now, what's the probability that uh, that um, so what's the probability that T is a valid tag for M? Well, M has at least one tag in, so M has at least one tag in this set, and we picked a random element from this set, right? So this probability is going to be at least is equal to 1 over n to the c, which is non-negligible. Okay, so whenever Tn is order log n, the adversary can succeed on like forging a tag by merely guessing the tag. And since the size of the set of possible tags is just polynomial, it's going to succeed with a probability that is inverse polynomial, which is non-negligible. So it has to be at least omega log n. But I don't see a way of proving that it's omega n. Because let's say even if it were like log square n, even then this guessing strategy won't work. So is this fine?
Okay. Sir, why you wrote order of log n equal to Cn?
Okay, so what do we mean when we say the function is order log n? For large enough, okay, so okay, let me write it. So we say this, right? Fn, in this case Tn, Tn is order log n implies there exists a constant Cz such that for large enough, for all n greater than, okay, there exists a constant and n0 in n such that for all n greater than equals to n0, t of n. So this is the definition of the order, like the big O notation, right? So over here, what I'm saying is Tn is order log n. It's Cn for large enough n.
Then for tn equal to order n, how to write, मतलब उसके लिए भी तो cn ही लिखोगे ना? नहीं?
Oh, sorry, sorry, sorry. Yeah, okay. C log n, right? Okay, this should be C log n. Yeah, yeah. Sorry. Yeah, this should be C times log n. Yeah, so two to the C to the log n would be log n. Like two to the log n to the C. That's n to the C. Yeah. So is this fine now?
Yes sir, yes sir.
Okay. Yeah. So let's look at the next problem.
तो सर ये n, अगर n लोगे तो उसमें तो फिर दिक्कत आनी चाहिए ना, मतलब उसमें तो आपने वही कर दिया ना, प्रूव किया था आपने, अभी क्या किया मतलब?
Right. So I proved that n would. Okay. उसमें गलती ये हो रही थी. If okay. So yeah, let me write it over here. So if it were n, you would have 1 to the 2 to the tn, but now it's 1 to the 2 to the c times n, right? But this thing is not this thing is negligible, right?
ओके, हाँ हमें नॉन नेग्लिजिबल चाहिए।
Right.
ओके।
And the reason this is not negligible is like this is like what? 2 to the c to the log n, that's 2 to the log n to the c, that's n to the c, right? Because 2 to the log n is n.
हाँ, और ये लेस देन नहीं है वन
Yeah.
अपॉन एन की पावर सी प्लस वन से, मतलब अगर बोले फंक्शन।
Huh. Okay, so is this fine?
यस सर।
Okay, so let's look at the next problem. This is similar to like problem 10. So consider the following map for messages of length ln equals to 2n minus 2 using a PRFF. On input M0, M1 and a random key k, the tag generation algorithm outputs Fk of 0 concatenated with M0 concatenated with Fk of 1 concatenated with M1. Is this max secure? So like what would be your guess after looking at question 10?
नॉट सिक्योर।
Right, and like can you come up with like some strings which the adversary should send the verifier?
कैन वी मतलब रोटेट दी, मतलब एक बारी ऐसे करेंगे एफ के जीरो एम जीरो और एक बारी एम वन कर देंगे उसको, ऐसा?
Okay, so what are you saying? Zero, like M0, M1 and M1, M0? Are you saying this? Are you saying this?
हाँ हाँ हाँ, यस।
Okay, and why would this work? Uh, 0 M0 we would get, 0 M1 we would get. Okay, so this can work, but then what would be, okay, let's say we send this, okay, let me just write this properly. Let's say we send M1, okay, sorry, M0 concatenated with M1 and M1 concatenated with M0. The verifier would send us two. So using these two tags, how would we construct a tag for a new message? Let's say I want to prove that this is not CMS secure. So how would I construct tag for a new message? And what would that new message be? Like you are right, you can use these two.
न्यू मैसेज में हम एम वन को पहले लिख लें, एम एम जीरो नहीं, ऐसा तो नहीं, एम
Like we
जीरो
have already
जीरो।
done that, right? Okay, here's what the new message can be. It can be M0 concatenated with M0, and the tag can be T11. Okay, so this is one candidate way of doing it. There are probably other ways of doing it as well. Okay, okay, so what's this probability? Okay, so a tag for M0 concatenated with M0 should look like FK. Yeah, M0 concatenated with Fk of 1 concatenated with M0, right? Now, T1 is a tag for M0, M1. So T1 is Fk, 0, M0, Fk, 1, M1, right? And what is like T2 is a tag for M1, M0, right? So T2 is Fk and Fk 1 M2, right? Okay, no, 1 M0. There is no M2 with you. Okay, let me bring this. Now this is our T11, this is T12, this is T21, and this is T22, right? So, and this is T11, T2. So, so T11
टी
and
टू
T,
वन आएगा, टी टू
oh,
वन
right,
है
right,
ना
right,
उसमें?
right, T21. Right, so this is the valid tag for this message M0, M0, right? Okay, 22 आएगा. It's going to be 22. Because one, like FK1M0 is over here, right? It's 22.
ओके ओके,
And
यस.
yeah. So now M0, M0 is a new message, and it's different from this and different from this. And we're able to create a tag for this. So this is not CMS secure at all. This is fine.
यस सर.
Okay, so I think we're out of time. So if you don't have any questions, we can meet next.
सर एक वो था कि ये जो आपने सारा लिखा हुआ है ना, ये आपकी स्लाइड्स नहीं मिल सकती बाद में, मतलब एग्जाम के लिए तो?
Oh, okay, I upload these as well. Okay, what I think NPTEL should have shared the folder with you. So it's a Google Drive folder. The NPTEL should have shared its link with you. If they haven't, what I can do is I can share it right now. You can share that link right.
ओके प्लीज.
So I put up all the like slides in this folder in the PDF format. So just like copy this before the meeting ends, otherwise this would disappear from the chat. Yeah. Are there any other questions? Because if there are no other questions, we can meet next week. Thanks.